Alright, welcome to week 8, lecture 1 of CS50DC. And if you remember yesterday, Mataza and Mr. Wood went through searching algorithms, and more specifically the binary and the linear searching algorithms. And today I'm going to take you through 4 sorting algorithms. And so it's fairly self-explanatory. A sorting algorithm is an algorithm that puts elements in a certain order, depending on what the user tells it to do. And so I'm going to introduce bubble, insertion, selection, and merge sort to you today. And so for the first 3, bubble, insertion, and selection, I'm going to use these music stands and these papers. So I'm going to need 8 volunteers. So if you 8 come down. And we're going to move on to bubble sort for the first time. So if you turn the papers around, you'll each have a number on it. Okay, so the pseudocode for bubble sort is basically you repeat it until there are no swaps in the list. And for I from 0 to n minus 2, if the ith and the ith plus 1 elements are out of order, you swap them. So I'm going to go through this fairly slowly. So we're going to get the ith element. So in this case, it's going to be 3. And we're going to compare it against the ith plus 1 element. So 3 and 5. Are these out of order? No, they're not, because 3 is smaller than 5. So then the loop is going to loop through it once. So then I is going to be equal to 1. So we're going to check 5 against 8. Is 5 greater than 8? No, it's not, so we're going to leave it as it is. We're going to go loop through it again, and then compare 8 against 6. Now, obviously, 8 is greater than 6, so they're out of order. And if you see on the pseudocode, it says we need to swap them. So you pick up your paper, and Harry, you pick up your paper, and you swap around. And we're going to do this for the 8th, 8 against 2. 8 is greater than 2, swap them around. 8 is greater than 7, swap them around. 8 is greater than 1, swap them around. And 8 is greater than 4, swap them around. And so the reason bubble sort is named bubble sort is because the elements sort of bubble up the list, depending on how big they are. And then so once that's done, we're going to go through it again. And compare 3 against 5, stays as it is. 5 against 6, stays as it is. 6 against 2, 6 is greater than 2, so you 2 swap. 6 and 7 stay as they are because 6 is less than 7. 7 and 1 swap. 7 and 4 swap because obviously 7 is greater than 4. And we go through it again. 3 and 5 stay the same. 5 and 2 swap because 5 is greater than 2. 5 and 6 stay the same. 6 and 1 swap. And then 6 and 4 will swap as well. So now we have 3 and 2. So this is the first time the 0th element in the list is going to switch. So 3 and 2 switch. 3 and 5 are good because 5 is greater than 3. 1 and 5 switch. 5 and 4 switch. And we go through it again. 2 and 3 stay. 3 and 1 switch. 4 stays. And then finally we're going to go through it again. 1 and 2 are going to switch. So as you can see, 8 started here, I believe, and it bubbled up. 7 started somewhere on this side as well, and it bubbled up, and so the elements bubbled up throughout the list, and eventually we ended up with a sorted list.
How does the computer know that the list is sorted now?
Oh, so as you can see, repeat until no swaps. So once we have a sorted list, the computer's going to go through it once again, and they'll say, is 1 greater than 2? No. Is 2 greater than 3? No. Is 3 greater than 4? No. So on and so forth. And once there are no swaps, the computer's going to say, okay, this list is sorted, I don't have to do anything with it. Any other more questions on bubble sort? No? Okay. So now we're going to go into selection sort. So if you guys go back to your original position, and I'm actually going to get rid of the music stands for this. Okay, so selection sort is, so you get this, the computer's going to look through the entire list of numbers that you have, and it's going to look for the smallest number. So in this case, it's going to assume that 3 is the smallest, 5 is the smallest, 5 is still the smallest, 5 is still the smallest, 2 is now the smallest, 2 is still the smallest, and then we get to 1. So 1 is the smallest. And what it's going to do, it's going to get 1 and 3, and the first element in the list, and swap them. So if you guys swap places. Okay, so now we know that this is sorted. This is basically the first sorted part of the list. So we're going to go through it again. And this time the computer is going to say, okay, 5 is the smallest, 5 is still the smallest, 5 is still the smallest, 2 is the smallest, 2 is the smallest, 2 is the smallest, 2 is the smallest. So 2 and 5, we're going to switch. And now we know that these two elements in the list are going to be sorted. So now we're going to go through the list again. 8 is the smallest, now 6 is the smallest, 5 is the smallest, 5 is still the smallest, 3 is the smallest, 3 is the smallest. So 3 and 8 are going to switch. And so we're going to keep going through that and through it. So 6 is the smallest, 5 is the smallest, 7 is the smallest, so 5 is the smallest, 5 is the smallest, 4 is the smallest, so 4 and 6 are going to switch. Over there. And we're going to go through it a few more times. 5 is the smallest, 5 is the smallest, 5 is the smallest, 5 is the smallest. 5 is going to stay where it is. 7 is the smallest, 7 is the smallest, 6 is the smallest, switch. 8 is the smallest, 7 is the smallest, you two switch. And now we know, once we've gone through the entire list, this list is entirely sorted and they're all in the right order. And if you look behind you quickly, that's the pseudocode. For I from 0 to n minus 1, find the next smallest element between the ith and the n minus 1th character, then swap it with this, swap the smallest number in the remaining list with the ith element. Any questions? Any question? Insertion sorts, if you go back to your original places. So insertion sort works as you get the number and then you insert it in the list in its right position. So the pseudocode for this is for I from 1 to n minus 1, remove the ith element and then put it into the sorted side of the list. So it's kind of easier to imagine this as the left side of the list is going to be the sorted side and the right side is going to be unsorted. So the first time through, the computer is going to say, okay, 3, you're now the sorted side, so you're going to move over here. 3 is the sorted side of the list, this is still unsorted. Then it's going to look for the next element, and say 5, okay, and then it's going to insert it into the sorted side, but in order. So 3 is going to stand next to 5, 3 is less than 5. So we're going to do that with 8, so 8 is going to move over. Is 8 greater than 5? Yes, it is. So now we've got 6, so it's going to take 6, move it to the sorted side, but it's going to put it in order. So it's going to put it after 5, but before 8. And then 2 is going to come over, and it's going to be put before everyone, and everyone moves up a bit.
How does the computer know where to insert it?
It compares the numbers in this list to the number that it is. So if it's 4, it's going to go, okay, is 4 greater than 2? Yes, it is. Is 4 greater than 3? Yes, it is. Is 4 less than 5? Sorry, 4 greater than 5? No, it isn't. So therefore, it's going to be put in here. So now we're going to move on to 7. 7 is 7 greater than 2, 3, 4, 5, 6? Yes, it is. It's less than 8, so it's going to be put in here. 1 is 1 greater than 2? No, it isn't. So 1 goes over here. Everyone moves up. And then finally, is 4 greater than 1, 2, 3? Yes, it is. It's less than 5, so it's going to be put in here. And that is how insertion sort works. So you guys can all sit down. Thank you for helping. Are there any questions on the sorts that we've just done? So if you remember what Mataza was talking about yesterday, the big O, it's the running time of the algorithm, how long it takes to complete a task. And for all three of these actually, the running time, the big O is n squared. And as you can see, as the problem is fairly small, it doesn't take much longer, but as the problem gets bigger, the time gets a lot, the time it takes to solve that problem increases drastically. And it's the same running time for all three of these sorting algorithms. And yeah, so now we're going to move on to merge sort. And this uses recursion, which Mataza talked about last Thursday, where it calls, yes, Mataza?
How come they're all big O of n squared if they're like different algorithms?
Can you answer that?
It's because even though they take different number of steps, the number of steps that they take depends on n squared. So it's the time that it takes is on the order of n squared, even though they might take different amounts of time, like actual amounts of time.
So like I was saying, merge sort uses recursion, which Mataza talked about. So it calls itself when solving what you want it to do. And surprisingly, the pseudocode for this is actually fairly easy. On input of n elements, if n is less than 2, return. So if the amount of elements in the list is 1, it's already sorted. There's no way that it can be unsorted. Else, sort the left half of the elements, and then sort the right half of the elements, and then merge them. So sort this side, and then put them in order depending on what they are. So I'm going to do a demonstration of this on the computer. It's a bit easier than having you guys all shuffle about. So imagine we're given this list of numbers: 87215463. So if you remember, it said sort the left half and then sort the right half. So we're going to concentrate on the left half. And I just put the pseudocode there so we know what we're doing. So then once we get to this, again, it's going to say sort the left half and then sort the right half, because we're calling the merge sort over and over again. So we've got this now, and we're going to sort the left half, and then we're going to sort the left and the right half. So what we've done is we've split these in two. So we've sorted the left half, then we've sorted the left half here of this, and then we've sorted the left half of that. And then now what we do is, when we merge the sorted halves, we have a pointer, if you like, sort of an arrow here, and then it's going to look, okay, is this element in this list greater than this element? No, it isn't. So that's obviously going to be the smallest element in it. So 7 gets put in here, is the smallest, and then 8 is here. And so now this side of the list is sorted. So now we're going to move on to the right side. We have 2 and 1, and then we're going to have 2 in one list and 1 in the other list. And then we're going to go again, okay, 1 is smaller than 2, so 1's going to go here, and 2's going to go here. So now that I've showed you this, can anyone tell me what the list is going to be down here, what order of numbers? Yeah?
1, 2, 7, 8.
Exactly. So we're going to compare the first number in this list to the first number in this list. 1 is going to be smaller, so it's going to be there, and we're going to go 2 is smaller than 7, put that down here, 7 is greater than 8, 7, 8. And so now we're going to do the right side. Oh, sorry. I did it for you because I didn't want to go through it all again. And then, so now we're left with 2 lists, each which has 4 numbers in it. 1, 2, 7, 8, 3, 4, 5, 6. And so now, it's going to have a like imagine you sort of have an arrow here and an arrow here. So it's going to compare 1 against 3. 1 is smaller than 3, so 1 is going to get moved down here. Then the arrow moves along. 2 against 3, 2 is smaller. 2 gets put here. Move the arrow along. 3 is smaller than 7, 3. And then we're going to have 4, 5, 6, 7, 8. And that's what you get. And so actually, the efficiency or the running time of merge sort is a lot quicker than the other 3 that I've shown you today. It's actually bigger with n log n. And if you put this on a graph and compare it with the other 2, as you can see, this is the one that bubble insertion and selection sort have. Big O of n squared. Whereas n log n obviously increases, but at a much slower rate. So as the size of the problem gets bigger, the time it takes to solve it doesn't increase that drastically. Are there any questions about merge sort? Any at all? I know it took me a while to understand it, so it's fine if you ask. No? Okay, cool. Yes, Mutasa?
How does it know when to stop?
Well, basically, if you look at this, it splits them into separate lists of 1 until there's no other way to divide it. So once it gets to this point, that's when the recursion stops, and then it combines them. And obviously, once you've taken all the elements out of this list, out of these 2 lists, there's nothing else to do, and therefore the computer knows that it's finished its job and the list is sorted. Any other questions? All right, thank you for coming. We'll see you next week on Monday during the workshop.